Hi, my name is Tiffany Edwards, and I'm going to be presenting the paper BlockQuery toward forensically sound cryptocurrency investigation. So this is a little bit of background on the authors of this paper. Tyler Thomas is the primary author. He couldn't be here today. He holds a bachelor's and master's degree from the University of New Haven in cybersecurity and networks. My name is Tiffany again, and I have a bachelor's degree in computer science from Southern Connecticut State University, and I'm currently working on my master's in cybersecurity and networks. And our mentor, Ibrahim Bagili, he leads our research team, and he helped us come up with the idea for this paper. Before I begin, I'd like to acknowledge the NSF for funding this research project, and I'd also like to say that any opinions, findings, and conclusions are not views of the NSF. So I will be talking about introducing this topic and talking about the motivation behind the topic, giving some background information, and then going over what we actually did to create this BlockQuery framework, and then discussing the limitations that we found, as well as future directions of this work. So to begin, we decided that, like every other investigation, forensic investigation, cryptocurrency investigations need to be forensically sound. And this includes completeness. Given a public key or wallet address, all transactions conducted using the key or wallet address are recovered. Integrity. The blockchain ledger being queried is identical to that which is currently accepted by the consensus network. And confidentiality. Information regarding which transactions are relevant to the examination are not being unintentionally disclosed with any third-party indexers or third-party organizations. We did find that the vast majority of publicly available tools that are currently on the market for querying cryptocurrency blockchains fail to meet one or more of the requirements that we have set forth here. So many tools take the form of websites which query a server running on a blockchain indexer and is often managed by a third party. This violates the confidentiality of forensic examinations by unnecessarily disclosing which accounts are subject to an ongoing investigations, which investigators would not want to happen. Also, without control of the indexing server, an examiner cannot guarantee the integrity of the query response. So the results may be inaccurate, incomplete, or out of date due to program error or malice, and can only be you can only confirm this by observing a local copy of the ledger. So cryptocurrencies, like Bitcoin, have many address derivation schemes, and many of the publicly available tools we tested failed to account for these differences in address derivation, which left out a lot of forensic information that investigators would find important. So because of these reasons, our motivation was to create a forensically sound cryptocurrency lookup platform that must consist of a trusted full node running directly on the blockchain network. This will allow forensic examiners to guarantee the integrity of the data that they are searching through by maintaining a complete copy of the ledger that is updated in real time. Also, the full node would preserve the confidentiality of the investigation by eliminating the need for a third party to handle the queries. And then instead of broadcasting the specific wallet address and transaction IDs that you're interested in, the full node would blend into the network and passively collect blocks as they are broadcasted. Our specific contributions are providing a primary discussion on what it means for a cryptocurrency investigation to be forensically sound, presenting BlockQuery as an open source proof of concept blockchain query system for Bitcoin. And we also show that our approach is capable of detecting transactions generated by the Hierarchical Deterministic or HD wallets that many publicly available tools cannot find due to failures in their address derivation methods. So some background to go over are the HD wallets. They use extended keys to compartmentalize addresses under logical accounts. They are very valuable artifacts in any cryptocurrency investigation because you can use them to derive the wallet addresses that are associated with the keys. Each account has an associated key pair, and the accounts are organized in a hierarchy. At the lowest level in the hierarchy, the keys are used to deterministically derive ephemeral wallet addresses. allow users to maintain relative anonymity across transactions by not reusing the addresses, while also being able to maintain only one master key pair. The forensic examiner could then use the extended public keys that they have to de-anonymize portion of the subject's transaction history for any wallet that they're interested in investigation. The Bitcoin blockchain uses 3 valid address representations. They have an XPub, YPub, and a ZPub. Each address type has a respective extended key representation that is used to derive addresses of that type. So these extended key representations can easily be converted from one to another, and one can deterministically derive all possible wallet addresses given any non-hardened extended public key representation. When performing memory forensic analysis of the applications using all 3 extended public key representations, we found out that not everyone used all three representations. For example, they would only use the XPub because they didn't know that there were 3 valid Bitcoin address representations, which left out information. So given that most query tools do not account for the fact that wallet addresses can use all 3 valid Bitcoin address representations, it left out a lot of information that is relevant to any forensic investigation. So to ensure the recovery of all relevant transactions, a forensically sound blockchain lookup service cannot assume that addresses should be derived using the same format in which their keys are represented. They should use all 3 address representations just to be sure they have all the information. So this slide just shows the XPub, YPub, and ZPub, and the example column shows their address representations. As you can see, they're all in different formats. And we did find that most query tools only refer to the XPub when they are trying to derive wallet addresses from the XPub extended key. So this slide shows what our BlockQuery looks like. We have a Bitcoin node, which is a standard Bitcoin JSON RPC API server that's fully synced with the current state of the blockchain. For this, we chose Bitcoin D as our protocol implementation for this for BlockQuery, and we chose it because of its ease of use, customization, and the integration into a variety of open source indexers. An indexer is a service that processes and indexes the raw block data from the node for quick and easy querying. It was necessary to use an indexer because we chose Bitcoin D, and Bitcoin D does not provide an API call to retrieve the complete list of transactions given wallet address participated in. For our indexer, we chose to use electors, and it was designed with privacy in mind, which just makes it better for the forensic examinations because it does not communicate with any third-party services. The web application is simply the user interface that is used for making queries and exploring discovered transactions. This was a custom application that was built to accept user queries, compute address derivations, and cache discovered transactions, and query electors at the same time. And we also allow users to input their derivation depth. So this slide has our algorithm for the address derivation scheme. The public key, either the XPub, YPub, or ZPub, is taken as a parameter as well as the desired derivation depth. Once the algorithm has that, a set of derived addresses are returned. Bitcoin uses change addresses with their wallets in an attempt to obfuscate outgoing transactions by generating new addresses on separate derivation path. They do this because they have an internal and external keychain. So addresses derived along the external keychain are intended for receiving transactions, and addresses derived along the external keychain are used for receiving transactions, and addresses derived along the internal keychain are used as the change addresses for other wallet functions that are not meant to be public. So for an examiner to have a complete understanding of how Bitcoin moves in and out of the wallet over the course of transaction history, you need to derive addresses along both the internal and external keychain. And you can do that by computing all the addresses derived in the X, Y, and Z pub format. So after all the set possible child addresses are generated, electors is queried with each address to retrieve the associated transaction history. This is done by brute forcing all the possible 2 to the 31 possible child addresses on the derivation path. It's necessary to brute force all possible child addresses because you want to make sure that all of the possibilities are found and are queried against the blockchain. So our tool allows the user to specify their depth of each query. So if they do not want to go through all 2 to the 31 possible child addresses, they don't have to. I also want to stress that hardened keys will stop the derivation. So the public keys are non-hardened keys, which is why they can be used in this algorithm and checked against the blockchain. At a certain level, the keys start to become the keys and their address representation start to become hardened, and you would then need the private key in order to get any more information from that. So this algorithm only works when you're given the extended public keys. Now I'm going to talk about our findings and our evaluation criteria. So we surveyed publicly available Bitcoin lookup platforms that were currently out at the time of writing this paper. We only considered services that allowed users to search for transaction by the extended public keys because that's what BlockQuery was made to do. Then we performed memory and file system forensics against each system to obtain forensic artifacts, including the extended public keys and the addresses. Then we also created a second wallet, which allowed the users to manually set the index of the derivation path. So all of the platforms were assessed for forensic soundness. The Bitcoin transactions were made using a Ledger Nano X cryptocurrency hardware wallet with a Ledger Live wallet software. I would also like to note that the BIP44 standard of Bitcoin defines the address gap for HD wallets at 20. It's possible to change to not use the standard of 20 for the address gap limit and change that number, and then you would then be able to hide addresses and transactions that associate with those wallet addresses in your blockchain. So to account for that, we tested each platform and including BlockQuery with address gap limits of 100 instead of 20. So we were looking at each tool to decide to determine if it was open source or not, if the tool queried a third-party server and thereby compromised the confidentiality of the investigation, if the tool automatically converted the key to every possible representation to cover the entire address space, and if the tool allowed the user to manually adjust the address gap limit or derivation depth. So this was a table of our findings. We surveyed 7 platforms plus BlockQuery, so there's 8 altogether. From this table, we found that Ledger's XPub scan utility was the only tool besides BlockQuery capable of finding all the transactions generated with extended public keys provided in the query, but it did lack confidentiality, which is very important for forensic soundness. And it lacks confidentiality because it utilizes Ledger servers to search the blockchain. It doesn't do it locally like BlockQuery does. And there is an option to use a different tool to search the blockchain, but that still doesn't prevent information disclosure to any third-party source. We also noted that the 7 platforms that we tested were not developed with forensics in mind, only BlockQuery was. So they had a lot of security issues, and 6 out of the 7 tools failed to automatically derive the SegWit addresses when provided an XPub extended key, and several of them were not able to discover the SegWit transactions even when provided all 3 XPub, YPub, and ZPub extended keys. So that left out a lot of forensic information. Our proof of concept was successfully able to discover all transactions while maintaining the confidentiality of the searches by not calling any third-party APIs and instead indexing the blockchain locally. A limitation we did find in our process was that If you did need to compute all 2 to the 31 possible addresses for a given extended key, it would require significant parallel computing power. At the time of writing this, the Bitcoin blockchain was approximately 350 gigabytes, and the Ethereum blockchain was approaching 1 terabyte. So we noted that smaller law enforcement agencies with limited resources may not be able to fully conduct cryptocurrency investigations with this platform. A solution that we did offer was outsourcing the responsibility to larger agencies that have the capabilities, or to trusted universities who can perform this step for them. Some future work that noted was that we had to create an extended key data set ourselves in order to conduct this investigation and experimentation. And we thought that if one was already developed, it would make it easier to develop more forensic tools that can help in cryptocurrency investigations. We also noted that since this tool, BlockQuery, was created for Bitcoin and only tested on Bitcoin, that the tool should be the tool should then be tested with other cryptocurrencies that implement address derivation schemes compatible with HD wallets. And from this we also noted that the other 7 tools that we looked at, and other tools besides those 7, they do the same thing that we do. They really only apply to Bitcoin, and they don't really apply to other cryptocurrencies. So we felt like that was missing in this research. And to streamline the investigative process even further, we considered making BlockQuery a plugin integration for certain software that already collects forensic artifacts, such as autopsy or volatility. So these are our emails. I'm open to questions now, and if I don't get to your question, you can contact any of us with questions that you may have in the future.
Thank you very much, Tiffany. Do we have any questions in the room or online? Don't see anyone here. So I have 2 or 3. How long would it take to do actually the brute force computations? Did you actually run them, or was it only like, okay, we would have to do them, and it's like 2 to the power of 31? Like, how complex is this computation that you actually run it? And are we talking of days? Are we talking of months? Did you do any more testing, like on the actual runtime?
Yes, that was handled by Tyler, and I'm not exactly sure the amount of time it took, but if I had to guess, I would guess definitely longer than a day, so maybe like a couple of days. I'm not sure what system he used to do that part of the experiment, or if he had like some tool that he was using to just make it go faster.
Okay, and just for clarification, the confidentiality aspect that you raised as part of your criteria, this pretty much equals that they did not operate on a local copy. Is that correct? Because they don't use, or these tools do not use a local copy, but they use like online systems.
Yeah, they use online platforms that store blockchain information instead of having the blockchain locally on their system. So that was the biggest difference when it came to confidentiality between our BlockQuery and the other platforms.
Okay, thank you. And I have one more. Is this publicly available or freely available? Is it like released on some kind of repository online, or is this some proprietary software?
Yes, it's on GitHub. The link to the GitHub is in the paper itself, so you can find it there.
Great. Are there any other questions in here? No? Let me check online real quick. There's nothing online. Then again, thank you very much, Tiffany.
I do see a question. Do you cross-out?
There is one online. Sit down. So
we didn't cross-validate the results with any other tools, but when we used those 7 tools, we noted that forensic information was missing. There was a previous paper that conducted memory forensics and analysis on blockchain itself. So when we did that paper, we noted that a lot of the other tools did not have forensics in mind, and they might have been missing information. So that's why we created this one, to gather as much information as possible. And we believe that we were able to get all the information that was necessary, especially since we created the extended key data set ourselves. So we knew what we were looking for.
Okay. Oh, now we have.
Well, I'm
You're
maybe
welcome.
completely talking, let's say, bullshit, but that's the problem always a bit. So I wondered, can you do this calculation without knowing the seed? So could you use it based on just the information on the blockchain itself, or do you need to have the wallet information as well?
Do I need to have the what information?
Well, my understanding of this hierarchical things is that you need to have the seed to be able to calculate all the other keys. And I think the seed itself is not stored on the blockchain. So can you do this calculation without having the seed?
Well, you need at least one of the extended public keys. They're public, so you should be able to access them on the blockchain, but you won't have the private keys. So that's why you can only do this calculation up to a certain level, because anything past that would need the private key. So there will be some information missing, but anything that's publicly available that you can get from any transaction history that's publicly available that you can get from knowing all the wallet addresses, you should be able to calculate them once you have at least one of the public keys. But it's better to have all three public keys.
Okay, I think then we got all questions. And again, then thank you, Tiffany, for your talk today.
You're welcome.